In this chapter, we are going to talk about simulation of continuous, discrete, and hybrid systems. In chapter 3, we have talked about continuous systems. Also, we have looked at some blocks and their applications. In this chapter, I want to do so for discrete systems. I want to show you some of the discrete library blocks. We will learn that how we can use discrete systems in our simulations. As you know, discrete systems have a lot of applications, so I'm going to explain discrete blocks library in this chapter. Then we're going to simulate a hybrid system which there are both continuous and discrete systems in it, which there are both continuous and discrete blocks in it. Okay, first I want to talk about discrete blocks. You can find its library here. As you can see, there are many blocks. The first block is delay. If you remember, we had this block in continuous as transport delay. But in discrete, we have it as z to the power of minus 2. I add it to the new model. Then I double click. Now, as you can see, here we can specify delay length or number of delays. The point in simulation of discrete system is sample time. Here, sample time specifies the steps in the simulation. Now, if I enter 0.1, the MATLAB performs the process of solving discrete equations based on this amount. For example, if I set the delay length 5, it means that the system has 5 units delay from that 0.1. I will talk about it more later. Here we have unit delay. It generates a delay in the system, but here there is the one sample delay and we can enter initial condition for it. Let's give an example. Pay attention that if I want to use transfer function here, it should be discrete. Also, we have some general blocks such as scope, mux, and demux, or sources and sinks. These blocks can be applied for both discrete and continuous systems. Now I add discrete transfer function. Then I go to sources and I add step. And then I go to commonly used blocks and add scope for mux. These blue lines can help us in decorating the blocks. In this example, I enter step to transfer function. I show its output with a 5-step delay and with a 1-step delay. I set the sample time 0.2. I do so for all of the blocks to have the same sample time. You can see other blocks that if they have sample time, enter that amount. But scope max and dmax doesn't have sample time and do not have effect on the simulation. The purple one is the response of system, the blue one is for the delay which we enter to the system. In the last signal, for 5 units our system had delayed. Okay, forward, and after that the simulation started. The point about system is that you can choose a variable sample time for delay. For example, I set it 0.5 and this one 0.30 around the simulation. Okay, now it has gone forward for 5 units. The other one has gone forward for 5 times 0.3 units. You can use delay in discrete systems. I save it as delay discrete. Also, you can use signal delay for sinus signals. How? I will tell it now. I choose a sinus wave. I set its initial condition 0 and sample time 0.1. I go to the sinus wave. This is a source block and we should specify its sample time. I set it 0.1. Now I run the simulation. Here we have a sinus signal with a 0.1 delay. It has not started from the beginning. We had set a 5-step delay, so the simulation runs like this. So we can use that signal delay for most of the sources. The other block is tap delay. It is very applicative. I want to talk about this block in the previous example. I want to use it in the previous example. But how does it work? Like previous block, we have initial condition, sample time, and number of delays. If you remember, we had number of delays in delay block. For example, if we entered 5 there, the block faced delay for 5 minutes. But here, in addition of doing it, each delay is displayed in a scope separately. How? For example, if I set the number of delays for every 0.1 step, the output will be shown in the scope. Now, if I simulate this file, you can see them in detail. For each unit that our system has delay, it is shown. As you can see, each unit that the system faces delay is shown in the scope. It was the method of working with tap delay in discrete systems. We have integrator block in discrete parts. The integrator block works same in the continuous and discrete systems, but the difference is that we can change the integration method in discrete systems. how it is in the integrator method in that block. There are 6 methods for modes of integrated in discrete systems. You can choose them and see the changes. You can use according to your projects. Again, we have derivative block. It's same with that in the continuous system. We have difference block here. I want to show it in an example. I want to have that model with pulse generator. This block subtracts the new input from the previous input by the sample time. I set its sample time 0.2. I set its period 4, amplitude 1, and pulse with 50. I want to show that how does difference block works here. When I click on the scope, you can see that the new input is subtracted by the previous input. How? The input which enters to the new part of sample time, we subtract it by that sample time, and then it is subtracted by previous input. You can see it here. If I enter lower amount for sample time, the output will be like in pulse response. Okay. Okay, we have discrete transfer function, discrete zero hold. We have it in continuous systems which work based on the system zeros and poles. We have transfer function real zero, which has real zero but not real pole. We have discrete filter, which have zero order hold function. Let's give an example about it. As you can see, this block has an input and output. This block shows the output in its sample time. Now, I should show it in an example. Let me add signal generator for this system. This block has a lot of applications in simulation of discrete systems. I use random waveform for in waveform. I set it random, amplitude 1 and frequency 1. I set this sample time 0.5. Now, as you can see here, suppose that the input is 0.01. It is kept constant as much as sample time, which was 0.5. Here, the system evaluates the input. The random signal that is yellow goes up for 0.44. Again, the signal is kept constant. Again, the system evaluates the signal because the input random signal is in this amount in the first second. And the process continues, so you can use this block in simulation of discrete systems. Now I think you're acquainted with applications of discrete blocks. There are other blocks too. Here we have discrete state space. I will explain it a bit later. Also, here we have transfer function lead or lag. Now, let me show you the application of state space block in an example. To display state space in discrete systems, we have such equations. The xt, which was in continuous systems, changes to xn here. And we have so for y. Just pay attention that this example is in the continuous form. First, we want to change it to discrete system with C2D code in MATLAB. After that, show it in the block. Here you can see the A matrices. It is a 2 times 2 matrix, matrix B, C, and D. Here, the D is the discrete sign. A and B can be displayed as AC and BC, which represent continuous system, and TS represent the sample time which considered for simulation in discrete mode. Here, I show the matrix A as AC. It represents the continuous state. I enter the amounts. The TS is the sample time. I set it 0.1 by C2D, which get the discrete modes of our system. The reason of this error is that I typed the matrix B amounts wrong. After entering the codes, you can see the discrete matrix here. AD is a 2 times 2 matrix and BD is matrix with 2 rows and a column. Now let's go to the Simulink. I want to show this example both in discrete and continuous modes. If you remember, in discrete mode, we had a state space block. Also, we have discrete state space. I want to show these two signals together in order to get a view on discrete and continuous modes in state space equations. And for discrete mode, we have discrete state space. I want to show these two signals together in order to get a view on discrete and continuous modes in state space equations. We entered the amounts. I said as I entered in the MATLAB A, C, and B, B, C. About matrix C, let me use from the example. It was 0 and 1, and matrix D was 0, 2. And we don't change the initial condition. We can enter A, D, B, B, D, and C and D. And we set the sample time 0.1. I do so for a step. As you know, because we have AC, AD, BC, and BD, I just entered their names in the blocks, and the Simulink itself recalled them from MATLAB workspace. After running the system, you can see the output. As you can see, the continuous mode is shown in yellow color, and the discrete mode is the shape purple one, which is following the yellow line with 0.1 second sample time. So as you saw, we can simulate systems equation both in discrete and continuous modes. Now I save this one as state space. Okay, now I save it as state space discrete. Let's work on another example. It's similar to what we had in simulation of multiple continuous systems. Here I want to show that kind of simulation in discrete systems. Also, I want to show a hybrid system in this example. First, I simulate the system in continuous form with using ZPK instruction, which is related to 0 pole. We have 2 poles in -2, 1 pole in -3, 1 pole in -10, and also the gain is 2. You can see the GS function here. There are 3 zeros and 4 poles. You can use state space or SS code. You can see the state space matrices here. A, B, C, and D matrices. Also, if you want to get the system equation, you can use C2D code 2. I set the sample time value 0.1. This equation is related to the system in the discrete mode, which you can see the zeros and poles of the system in this mode. Pay attention that the codes which were in continuous systems exist in discrete systems too. For example, in order to get GD transform function, we can use this instruction. Again, you can get this state space using SS code. And also you can see the A, B, C, D discrete matrices. Also, you can simulate each of these modes with using discrete blocks of Simulink. In the previous example, I explained the steady space block, but in this example, I want to use discrete zero pole to create the model. I want to show both discrete and continuous systems in a single simulation file. Like previous example, I simulate the model. I enter the zeros and poles of the system, and you can see that the output is same as the continuous system. I enter the zeros and poles of system, and you can see that the output is same as the continuous systems. Based on zeros and poles of continuous mode, as we entered in the matrix of system, we had 0 in -1, -4, and -15. About the poles, we had 2 poles in -2, 1 in -3, and 1 in -10. And the gain was 2. If I enlarge the shape, you can see zeros and poles of the system. About zeros and poles of discrete mode, we can use the zeros and poles of system. I set the two blocks. I set the sample time 0.1. Now the simulation of two systems are same, and the discrete mode is changing by 0.1 sample times. Okay, I save it as zero pole discrete. Now I'm going to talk about hybrid systems. Simulink can combine the different times of sampling. It can use as both discrete and continuous blocks in simulation. Let's give an example. I use both transfer function of discrete and continuous. Also scope for showing the output. I want to have a feedback system. And the step, I add a step 2. Here we have both discrete and continuous. Here we connect the discrete transfer function to the continuous transfer function. We have a scope for showing the output and sum for using the feedback of system. I set the sample time 0.1, it's for I set the discrete sample time 0.1, and I do so for step 2. Now I run the simulation to see the output. Now as you can see, discrete and continuous modes were combined. A hybrid system has been made. Now I change the feedback to negative and then see the results. So Simulink can be used for hybrid systems too, both discrete and continuous systems can be simulated in hybrid systems. Okay, now I save it for you as hybrid. Okay.